Hello, my name is Alexander Sejovic and I am Oracle Coherence Architect at Oracle. In this video, I will walk you through Helidon Sock Shop demo and explain why it is significantly simpler and easier way to build microservices applications. So let's start with what is Sock Shop. So Sock Shop is a microservices demo application that was created a couple of years ago by Weaveworks, and they were gracious enough to open source it under the Apache license so others can implement it using different technology stacks. So the original application, or actually any Sock Shop application that implements the architecture defined by Weaveworks, consists of a front-end UI and 6 back-end services. These services are shopping cart, orders, user service, product catalog, and then payment and shipping service. So the original implementation uses different technology stacks to implement these services. Some services are implemented in Java using Spring Boot, some are implemented in Go, and then they also use different backend stores. So they use some of them use MongoDB, some of them use MySQL. Front end actually can use Redis for HTTP state management, and the front end itself is implemented as a Node.js Express application. So it's a good example of a polyglot microservices implementation, and as well as polyglot persistence. So let's look at the original application just to understand what it does. So I have this application deployed under original Sock Shop Helidon.io, and I can make sure I'm logged in. So I can log in, and then I can browse product catalog, add items to shopping cart, see the contents of the shopping cart, and then add shipping address, payment. I already have them set up, and then I can proceed to check out and submit the order. So the order has been submitted, and I can view the order. Right, so that's basically all the application does. So all of these 6 services, they're deployed as separate pods in Kubernetes, and they're interacting to allow you to browse product catalog and submit the orders. So that's all good, but there are some things that are wrong in this application. For one, this application is obviously completely functional, right? We've seen that it works, but when you dig a little bit deeper, there are some things that are not quite as they should be. For example, are these services truly scalable, right? We know we can scale stateless services, Spring Boot services and Go services easily. But what about data stores? Can we scale Mongo, MySQL, and Rabbit as well? Are they highly available? And are they easy to monitor? So unfortunately, the answer to all these questions is no. And the reason for that is this. I mean, the way these applications are deployed, all data stores are basically just there so the applications can process requests. If you look at the Kubernetes deployments, you can see that both the services and their databases are deployed as Kubernetes deployments, not stateful sets. So yeah, and if you look at the number of pods, each of them has a single pod. So while the services such as carts, catalog, orders can be scaled easily using Kubernetes, we can't really scale database components that easily. So the other problem is because we can't scale them, we only have one of them. They're not actually persisting to disk, they're just storing everything on the ephemeral disk. So if we lose any of them, we're not only going to make application unavailable because we're not going to have data store anymore at all, we're also going to lose the data in the process, because when we restart the database, data is not going to be loaded from persistent from disk, and it's going to be empty. So how is that? How is our application better? So we did what we did in a Helidon and Coherence workshop implementation. We effectively changed the architecture a bit. We used Helidon to implement all the services, all the REST endpoints and GRPC endpoints for some of the services. And then we use Coherence as a data store. But the difference in this case is that Coherence effectively becomes embedded data store that is also clustered and can be scaled out just as easy as any stateless service. So, and in order to do this, we're basically using a number of integrations that we've implemented for Helidon and Coherence to make them work well together. For example, we are using CDI to bootstrap Coherence within Helidon application and allow effectively Helidon processes to form a cluster. And then inside of that cluster, inside of those processes, Coherence is available to provide data stores to Helidon services, to provide Coherence maps that are clustered, scalable, fault tolerant, and also can be persisted to disk. We're also using metrics integration to make Coherence metrics and application metrics available in a single metrics endpoint, which is exposed by Helidon and can be scraped by Prometheus and then consumed by Grafana or any other dashboard. We also have integration with microprofile configuration, which allows us to use Coherence as configuration source and also to configure Coherence itself using normal Helidon configuration. So that makes configuration of the application as a whole much easier than if we didn't have it. And then last but not least, we have completely seamless tracing integration. Both Helidon and Coherence use open tracing. And what effectively happens is you can see the request all the way from the service, from the API, from the REST API or gRPC API, through the application components such as repositories and services and whatnot, all the way down into low-level internal Coherence components. So you can see exactly how the request is processed in Coherence when it goes to fetch the data, to aggregate data, when you store data, how the backups are sent to different Coherence nodes, etc., etc. So let's look at Coherence implementation. So now we're gonna, it should look very similar. So it's the exact same front end. We actually use the exact same front end, the same Docker image, same container that the original application uses, but all the backend services are different. So let's log in again. And then we can browse the catalog. We can add socks to cart, go to cart, proceed to checkout, and again we can see the order. And the IDs are slightly shorter because our implementation shortens a bit, but you can do exactly the same things. The front end is driving. The backend services are implemented exactly the same as the original ones, so you end up getting the same functionality. But how is this different from what we've seen before? Well, if you look at this, we have all these deployments. So we have this is the original SockShop application. So if you look at deployments that we have here, we have one deployment for service, we have one deployment for database, and they're all deployments. And if you look at the pods that we have, you will see that we have one pod for each deployment. So there is cards pod and cards.db pod, catalog DB. This is different from the Coherence-backed application. First of all, we are using Coherence operator to deploy different Coherence roles. So when we search for different Coherence deployments, we'll see that we have cards deployment that belongs to SockShop cluster, and it has a roll of cards. And at the moment, it has a single replica, which is ready. And we have one of those for each service. And then each one of them is effectively backed by a stateful set. So you can see that we have cards, catalog, orders, payment, shipping, and user stateful sets, and they have one pod at the moment. And if we look at the pods, you will see that instead of 2 pods per service, one for service, stateless service, and one for the backend for the data store, we actually only have 1 pod per service. So as I described earlier, Coherence is embedded, Helidon is driving the API, Coherence is used to store the data. They belong to the same pod. They're actually in the same container. You can see that we don't have multiple containers in the pod. There is only one container, one JVM per pod at the moment. And the application is fully functional. It stores the data. It can actually persist data to disk because we are using stateful sets. And we can shut the whole thing down, bring it back up, and the data will still be there. But this is still not, so that's, obviously, it simplifies architecture a bit, but by providing less components to kind of worry about. But is this scalable? Is this highly available? And how easy this is to monitor? Same questions that we asked about the first application. So it is scalable, and at the moment it is not highly available. And the reason it is not highly available is that we only have a single pod for each service, right? So if any pod dies, it will get restarted, but until it gets restarted, that particular service is not going to be available. So the way to fix that is actually to scale out. And the way to check the state of our pods is to look some of the management features, some of the operational features that will tell us exactly what is going inside of our clusters, how many members we have, how many endangered services we have, et cetera, et cetera. So to get an idea of what's going on, right now we have 6 cluster members, right? And that's exactly what we expect. We have 1 member for each service, 1 pod for each service, so that's 6 cluster members overall. And we can see here that we have 12 endangered services. And we can also see that we have 19 gigabytes of heap available across the cluster, because we're starting these cluster members with a 3 gigabyte heap allocation. They will basically have 18 to 19 gigabytes of heap altogether. And if we look at services themselves, we will see that services right now are all endangered. So we have 12 services that are all endangered, except for the config service, which is actually automatically spread across all available members. So that one is marked as machine safe. So let's fix that. And to do that, all we need to do is scale this cluster, or scale these to at least, scale each of the services to at least 3 members. So let's do that. So this is basically your standard kubectl scale, and we are telling it to scale Coherence deployment for each service. And you will see as a result, it says that cards deployment has been scaled, orders has been scaled, catalog, payment, all of them should be scaled to 3 members. And it will take a little bit for all of them to start. But if we look at Coherence deployments now, we should see that each one has 3 replicas. Only one is ready at the moment, but in a minute, all of them should be ready. And if we go back to Grafana, you can see that some of the services are already site safe, that they see 3 members, and then the rest of them should become site safe in a minute. And the same thing, so yeah, so now all the services are site safe, and you can see that we have 3 members for each service. And if we go back to the main dashboard, we should see that we now have 18 members, and those 18 members now have 3 times as much space on heap as the original cluster of 6 members, because we just added We just added 12 more members and increased the capacity of the cluster to 58 gigabytes. So that's all good, but scaling to 3 members per service is actually not that exciting. So let's do something more fun. And scale to 40 members per service. That should give us a cluster of 240 members in a reasonable time. It will take a few minutes for it to be scaled, but until that happens, we can look at some other observability features. So, as I said earlier, one of the integrations that Coherence and Helidon have is the open tracing integration, and you can see that in these traces. This is a very simple trace that actually does a GET request on the user object. So you can look at beginning root of the trace to see that it came to Helidon web server. It was GET request with a status code of 200 to endpoint customers Alex cards. And that request was then checked by Helidon security, authorized, and then eventually delegated to the business, to the JXRS resource customer implemented, that implements get customer cards method. So that handles the actual request. As part of the processing, it calls user repository get user, which then executes get request against Coherence. So again, this is still Helidon trace, and it basically just traces a method in this particular class, and that class makes get request to Coherence. So you can actually see here that this span came from Coherence itself, because it came from user service component. It was executed on a cluster member 6. This is the Coherence class that executed the request, and this is the thread that the request was executed on. And then that request was sent into dispatch into a cluster and processed, in this case on the same node, because this is when I had only a single node, single cluster member for each service. So you can see that the response, the GET request was processed by member 6 and partition 22. That's where this particular key that was requested belongs. So this is a very simple GET request, and we have a similar simple query request when we only had single node, single member in the cluster. You can see that request came to Helidon web server catalog with some parameters, page 1, 6 elements to return, and that was then sent to catalog API get socks JXRS resource, which in turn called Coherence catalog repository get socks method, which executed query request against Coherence. So again, single trace spans from both application itself, from Helidon and from Coherence are fully integrated. And we can see that in this particular case, query request was executed on member 5 from Helidon 3 thread, and then the actual processing of the request happened also on member 5, because again we have only one member per service at this point. You can actually see the filter that was sent to Coherence, and you can see that the partitions 0 through 256 were processed on the catalog service worker, one of catalog service worker threads. So that's basically all the way from the REST API down to the storage tier, storage in Coherence. But these are not very interesting traces because they only have a single member. So let me show you a trace that was similar to the previous one, except it did aggregate request against a cluster that has 3 members in it. So as before, we can see that the request came to catalog size endpoint with some tags, and we wanted to get the number of products that satisfy the criteria. Ultimately, that ended up hitting catalog API getSoCount method on JXRS resource, which then called Coherence catalog repository getSoCount, which then dispatched this request to 3 members that were available. So for each of these requests, we can now see that it was sent from member 12 on this thread. So all 3 of them were sent from this member where this REST request happened. But they're all processed on different nodes. Because if we look at process information, we can see that this particular request got processed also on member 12 on the local member, and it basically returned results from partition 0 to 41 and 128 to 171. But then the other 2 requests were processed on different members. So this was processed on member 11 for a different set of partitions on a different thread. And the last one was processed on member 5, again for a different set of partitions. So basically, what Coherence did in this case is it submitted the submitted query to all the available members and processed it in parallel, and then returned the results to the client. And you can see that quite easily. If we close all of these, you can see that the request was submitted and processed in parallel across different members, across different data centers, actually in this case, and the result was then returned to the application. And finally, let's look at the example where we actually did some writes, because all the previous examples were reads. So this is the order processing endpoint, probably the most complex piece of functionality in the application. And you can see that, again, the request came to Helidon application, Helidon endpoint, as a post request to orders endpoint on this particular host. It was handled by orders API new order method, which then made couple outbound requests to other services. So it made requests to the cart service to get cart items for the user. And then it made requests to the user service to get the address for a customer, as well as credit card to use for payment, and finally the customer information itself, right? So these requests were made, I mean, we could have technically made these requests in parallel. The implementation right now does them sequentially, and you can see that in the timeline. So there was some initial processing, and then we made requests, this was called to the shopping cart service, and then 3 calls to the user service. And then finally, we are making call to Coherence to actually store the orders that we are trying to process. So we're calling into event-driven order processor process order method, which then calls Coherence order repository save order. And now we see that there is a put request that is being made to Coherence from Helidon thread on member 1. And that put request is then processed by member 10 on a Coherence worker thread. And then finally, that put is actually backed up to a different member, and backup from member 10 is processed on member 1, and then the control is returned to the client. So once we put the order into Coherence map, it will be processed on a primary member and then backed up to another member. So again, the point of this is that you have a full visibility all the way from the REST API endpoint down into the Coherence storage components. So let's see where we are with our scaling. Okay, so we are up to 40 replicas for each service. All 40 are ready. And if we go back to Grafana, we can see that we have It may take a minute to update all the information, but we do see that we have 240 cluster members. Total cluster heap should increase significantly once Grafana gets updated. Until that happens, we can see that on our services dashboard, we can see that each service now has 40 members. It is still site safe, and because config is spread across all the members, it actually has 240 members in this for this particular service. So we go to main dashboard. Seems to be lagging behind a bit. Well, we'll come back to it. All right, in the meantime, let's go back to the presentation and look at some additional things. So, no more dragons. I mean, the implementation itself is simpler. We haven't looked at it. We will in a minute. But we basically ended up with stateful microservices that are as easy to scale as the stateless one. You saw that there are no separate data store pods. We are effectively using same set of pods both to manage data and to process incoming requests. Now, we could separate them out. I mean, this is the simplest model. If we wanted to, we could separate them out, define different roles that will be used as application servers to process incoming requests, and the other roles, the other sets of members that will be used as storage nodes. We could also split each service into a separate cluster. There are many different options we can use, but this is probably the simplest and easiest model to start with, and then nothing in the application needs to change if you want to use a slightly different model. High availability, because we can scale out so easily. The high availability is effectively built into the architecture. All of those pods that we created are stateful pods. They persist data to disk. If we lose any of them, the backups will be restored, the data will be rebalanced, new backups will be created. If we scale out by adding more pods, the data will simply be rebalanced. The system is operational the whole time. It can process requests and continue as if nothing is happening in the background, even though new members are being added and the other members are, some members are being removed, or the data is being rebalanced. As you can see, support for monitoring is also built in. There is a set, I mean, we saw only a few dashboards, but there is a fairly large set. There's like a dozen or more dashboards that allow you to see different coherence metrics, and then you can also see the application metrics, which is something I didn't really show and probably should. So this dashboard finally updated, and we can see that now with 240 members, we have 773 gigabytes of space, which is what we would expect to happen, right? But we also have the dashboard for the application itself, which allows us to see application metrics that Helidon exposes, right? So we can see that we processed 2 orders total. We are not processing many orders, so the rate is fairly low. The average order processing time was 38 milliseconds, and then we had 2 successful payments, right? And remember this, because when we look at implementation, we will see where this is coming from. So that's the dashboard that we created for the application itself. So this is a custom dashboard for metrics that are exported from Helidon. So let's look at the implementation. Obviously, we suggest that you go to GitHub and get the source code for the whole application. It's all documented, how to set it up, how things are structured, etc., etc. So if you start using the link at the bottom of the slide, you can basically deploy application locally, clone the repo, deploy the application locally, run it, play with it, etc. It also tells you how to deploy it in a real Kubernetes cluster in the cloud, which is similar to what I did, in which case you can set up ingress controller, you can set up Jaeger, Prometheus, Grafana, all of those things are documented, so it will help you get started. So until then, I do want to point out a few features, few implementation details that show how much easier it is to write applications using Helidon and Coherence together. One thing that Coherence gives you is the ability to store Java objects. There is no impedance mismatch, and you don't have to store dumb data objects. You can actually store rich Java domain models, and you can use those Java domain models. So you can build fully functional domain-driven applications that are distributed, fault-tolerant, scalable, using combination of these two technologies. So let's look at a code example at the bottom of the slide. So the first step we have is we inject Coherence named map that holds shopping carts into a local field. This is code from the shopping cart JAX-RS resource, REST API. And then we implement the add item method, which allows us to add item to a shopping cart by using in-place processing with Coherence. So we are calling invoke method on the shopping carts map on the cart ID that was passed in. And then the second argument to invoke method is a Java Lambda that will basically be serialized on the client, sent into the cluster, and executed on the node that actually owns this particular shopping cart. So we're, instead of fetching the cart from the data store and updating it and then sending it back and dealing with all kinds of concurrency issues across cluster of, at this moment, 40 nodes per service, we're basically changing things around, and we are sending the code to execute to the owner of that particular shopping cart, which there is only one in the cluster. So that gives us local atomic transactions that are very efficient, very scalable. We can send many of these entry processors across the cluster at the same time. It reduces the amount of data that we have to move over the wire, because we are not moving the actual cart. We are just sending a piece of logic to execute on the cart. And then what it also allows us, if you look at the code inside of the Lambda, is we get shopping cart from the entry by calling getValue method. And then in the second line, we call basically a domain method on the cart. This add method will either add item to the cart if item with a particular, if the same ID doesn't already exist, or it will increment the number of the quantity of the item if the item with the same ID is already in the cart. So that's kind of very basic, very simple domain logic, but it is domain logic that the shopping cart class implements internally. And then we simply update the value by setting new shopping cart as the value of the entry and return the item, because that's ultimately what this method needs to return. We want to return the item that was added. So that's an example of how we can efficiently do updates and use rich domain model in the cluster to do so. The second example is event models. So one of the things we did with the Coherence implementation of Helidon SockShop is to use Coherence server-side events to implement order processing. So instead of trying to do everything synchronously when the order is submitted, we basically put order, save order in the Coherence map with the status of created, and then we use CDI observers to observe entry inserted or entry updated events on the orders map. So when those events happen, which is whenever the particular order changes, we get the order from the event and then we check the status. If the status is created, the first step is to process payment, which will either succeed or fail, and then it will update order status to either paid or payment failed. So if the order is paid, in the next step we'll receive another event that the order was updated, and we will see that the status is paid, and then we will call shipping service to ship the order, which will again update order status to either shipped or shipment failed. So this way we can basically update order based on its status and do it completely asynchronously and increase the performance of the front end. It's also more reliable because you don't want to do all of these things synchronously, because if the payment failed, you probably want to have something else happen to either send email to the user to update credit card information, or or something else. So this allows you to handle that in an event-driven way. And last but not least, this is not really coherence specific. This is more Helidon. One of the features that Helidon has that that none of the other popular microservices frameworks have at the moment is the ability to implement GRPC services in addition to REST services, which is very powerful. They're lighter weight. They use binary transports. They can stream data back, etc., etc. There are many benefits to GRPC. However, GRPC is not always the easiest thing to use. For most GRPC applications you will see out there require that you implement proto files, generate classes, use those classes, etc., etc. So it can get fairly complex to set up and to use, and there are many limitations when you use protobuf generated classes. In this case, we are using we don't do any code generation. Helidon basically provides a framework similar to JXRS that is used to create gRPC servers and clients. So on the server, we basically annotate a class with @grpc. We specify the marshaller. In this case, because we already had all of this working via REST and we use JSON for serialization, we simply switch marshaller from a default, which is protobuf, to JSONB. So we will use JSONB for serialization just like our REST services use. And then we mark the methods just like you would mark JXRS methods with get or put or post. You mark methods here with either @unary or @server streaming, client streaming, or @bidirectional, which are 4 different method types that gRPC supports. And then you simply implement the methods just like you would implement your JXRS methods. And Helidon gRPC framework will take care of converting whatever the return value is into to sending it to appropriate stream observer under the hood. And also, if you want to make this service asynchronous, all you need to do is basically to change return value from whatever it is now to completable future of the completable stage of the same thing. So if we change this to completion stage of collection authorization, completion stage of authorization, these services would effectively become asynchronous. And then similarly on the client, just like you can create REST clients by defining an interface and adding few annotations to it, you can do the same thing for gRPC. So in this case, we're saying that we want to create client for the gRPC service payment gRPC, which is the name of the service we created in the previous step. It's automatically defaulted to the class name unless specified explicitly. So we want to call payment gRPC service. We want to use payment channel, which is either a host name or a Kubernetes service name in this case, or a name of a configuration element that specifies which host and port to connect to, which gRPC server to connect to. And then finally, we have the same marshaller annotation that we had on the server, which has to match in order for a client to be able to communicate with the server. And then in this case, what's important, even though we had 2 methods on the server, we only need to define the method that we actually care about. In this case, because we use this within order service and we only ever call authorize method on the payment service, we only need to add authorize method to the payment client. And you can also see that the actual return value and parameter, well, they have to be compatible based on whatever marshalling format is used. They don't have to be the same. So here we are returning payment, which is a class that belongs to order service, while the actual server implementation is returning authorization. Those are 2 different classes in 2 different services. There is no shared data classes. It's just shared JSON payload between the services, which happens to have the format that both these classes understand. And then finally, we use this gRPC client in our service by simply injecting. We can say @inject, @grpc proxy, specify payment classes interface, and the appropriate client instance will be created and injected for you. So those are some of the interesting bits of SockShop implementation. To learn more, about Coherence, you can go to coherence.community. And if you remember one links out of these, that's the one you need, because that one has at the bottom of the page links to all the rest of them. But you also have a link to our blog where you can find more information, and if you follow it, you will get updates as new articles and blog posts are released. You can, of course, go to GitHub and get Coherence source itself. And there are many videos on the existing Coherence YouTube channel that will give you more details about different features. And finally, if you want to connect with us and chat with us directly, you can join Oracle Coherence Slack channel. Thank you very much. This concludes this presentation. I hope you enjoyed it and it was useful, and I'll leave it to this. Thank you.